Okay, you have our traditional 5-minute delay. So it's today. Today is the last seminar in 2014 year, and we will resume again in January after people will kind of relax after SkyTech meeting. But today to have a good finish, good exclamation mark for 2014 seminar series, we have our speaker, Hiro Nishikawa, and in recent days there were many discussions about the importance and benefits to have high order and in particular third order schemes for various aerodynamic computations. So today Hiro will present his developments on some third order scheme, which is a finite volume scheme, which is very attractive in my view and has a great potential to be combined with modern state-of-the-art CFD solvers. Thank you very much. Take over.
Thank you, Boris. Thank you very much for coming, and thank you very much for watching. I'm going to talk about this accuracy preserving something. It's based on the journal paper published recently, very recent. This is 2015. And and the holiday season is coming, so I'd like to add a little bit of a holiday taste to this talk. So the main theme of this seminar is actually this. You already have it. This is an idea that can be found everywhere, like inspirational, motivational speeches and books, and perhaps in folklore in every culture. It basically says, whatever you need, you already have it. You want happiness? You already have it. You want a job? You want money? You already have it. You want a Ph.D.? You already have it. It sounds crazy. And I know you say, no way, I don't have what I don't have. But this is actually true. The issue is always just how to manifest what you already have. You just don't see it. You just don't know it. For example, I'm thirsty. I need something to drink. And I see a bottle of water right here. So I already have it. But what if the bottle of water is behind me? I have to turn around and see a bottle of water. And then I say, I already have it. But what the problem is, what makes me turn around? A belief. You have to believe it. You have to believe you already have it. And then you take action. So the first step is always to believe it. If you don't believe it, you don't find it. You sound like a preacher. I'm talking about theory. So in this seminar, I'd like to demonstrate that this is true in CFD. Okay? So I'm going to talk about edge-based discretization. This is the target.
I like this connection.
So edge-based finite volume, the node center, the solution lives at the node, and we have dual control volume. And this is widely used formulation, NASA Fund 3D, Sophia Cradle, SC Tetra, via Talcott, etc. Many code uses this edge-based finite volume. And here's a steady conservation law. And as I will explain later, this steady conservation law represents the various types of PDEs, so including nuggets. And edge-based finite volume looks like this. This is a dual volume, Vj. And then this is the sum of the fluxes. The flux is computed at h midpoint and multiplied by this directed area, which is the sum of these two pieces. So one flux per edge. This is the edge-based formula. And I consider numerical flux, which is upwind, but it doesn't have to be upwind. What is important here is that it has this consistent approximation to the flux, physical flux, and then you have dissipation. And the accuracy of this scheme is determined by how you get these left and right states. You get first order accuracy with nodal values. It's just with uj and uk. And second order with the linear extrapolation to the h midpoint using linear least squares. And surprisingly, this achieves third-order accuracy with linear extrapolation in the solution and also in the flux using quadratic least squares. And this is a great discovery by Katz and Sankar. And this is true only on triangular mesh. So this is a very efficient third-order scheme because it can be implemented as an edge loop and just one numerical flux per edge. And I'd like to show, before I talk about boundary formula, I'd like to show why this is third order. So we have, this is part one, I have another slide. But first I'd like to show that the zero, for quadratic solution, it gives zero dissipation. So linear extrapolation with quadratic least square gradients, these are the formula. The left state coming from node J and right state coming from node K. And these solution gradients are computed exactly for quadratic solutions. And you can show the detail in the paper, but for quadratic solution, these formulas give identical value at the edge midpoint. But as I write here, this is not exact for quadratic function. Okay? If it is exact for quadratic, then it must have some curvature term. So it is exact only for linear function. But then, because they are identical, the dissipation vanishes. So if there's any error committed by this edge-based scheme, it must come from this average flux. So let's look at this average flux. So for third order, we need to do this linear extrapolation of fluxes. In the same way, you can show for quadratic flux, these formula, the linear extrapolation gives identical values at the edge midpoint, but not exact for quadratic. But then, this edge-based scheme, this is a numerical flux. Because dissipation is zero, we have only this average flux. And average flux is this. So we have this equation for the edge-based scheme.
I would just remind, this is an informal seminar. If you have a question, ask right now.
Yeah. So the first term, okay. Yeah, first term is.
What do you believe?
I will talk about this later. So this is Fj. This is just a constant. And so sum of the directed area, which must be zero for closed volume. And this second term, this is gradient. And you can show that on triangular gradient tetrahedron, this becomes exactly the divergence of F. So for quadratic fluxes and quadratic functions, this edge-based scheme gives exact divergence. So it's exact for quadratic fluxes, and that's why it achieves third-order accuracy.
So I understand what you mean by linear reconstruction.
Mm-hmm.
When you say quadratic reconstruction, are you doing linear quadratically, or you're fitting the data quadratically but only using the linear part of it?
Yes. Okay. So to compute this flux gradient, I assume that flux is quadratic, so, and then exactly produce this gradient. But I use only the linear extrapolation to get the phase value. You know what I mean? And it has to be exact, this gradient has to be exact for quadratic to get this expression and to get exactly the same value at the edge midpoint.
So to create the gradient of the flux, you're doing a quadratic fit.
Mm-hmm.
But then for the flux extrapolation of the phase, you're doing linear.
Yes.
Using that gradient you've got from the quadratic.
Yes.
Okay.
And here you're actually extrapolating the flux, not the primitive variables that go into the flux.
No.
That was part one.
Yeah. But I will show that this gradient of flux can be computed from the solution gradient using chain rule.
Sure.
So now, an interesting question to ask at this point is, okay, what if I use quadratic extrapolation? What if I can produce exact flux for quadratic function? So here's the, there are ways to do it. You can do quadratic extrapolation, or you can use kappa 1/2 in new muscle. And with gradient, exact for quadratic function, you can actually produce exact phase value with kappa 1 half. So in this case, the flux left and right, again, they are identical. But they have now this curvature term, because this is exact for quadratic function fluxes. And then you plug this into edge-based discretization. Now this average flux has one extra term that is proportional to the curvature. And this term doesn't go away. This is order h squared. And this is order h divided by order h squared. That gives you a first order error. Oh. So first order truncation error implies second order discretization error. So if you produce exact flux for quadratic fluxes, this edge-based scheme loses third order accuracy. So when you do this third order edge-based scheme, do not use quadratic extrapolation, do not use kappa 1 half. And I actually tried it with my Navier-Stokes scope, and I saw second order accuracy. And it was very strange, but now I understand why. It shouldn't be very accurate. It's strange. But anyway. So far I've talked about steady conservation law, and this is first order accurate and second order accurate and third order accurate. And here is the chain rule. Yeah.
Hiro, so sorry. Yesterday, we saw a presentation where they talked about kappa 0.5, right? Were they claiming that it was third order accurate?
No, they are not using kappa 1 half.
Okay.
They use something else. Something corresponds to kappa 1/3.
Okay.
Yeah. I don't know how kappa 1 half scheme is useful.
I thought it was a kind of something to get defect correction to work when we first went to mixed elements. I thought that's what it or when we first started getting used.
Because kappa 1 half is capable of producing exact point value from point value for quadratic function. And that's not very useful in finite work. In cell-centered scheme, what you need is a point value at the face, but you have cell averages. And in that case, you can use one cell to produce accurate point value at the face. And yesterday, their scheme is also exactly the same. What they need is one cell to compute primitive function of your flux at the face. That's basically a cell-centered scheme. And this is all based on the point value. It's like a finite difference. Anyway, so far I talked about steady conservation law. And of course, for Navier-Stokes, we need viscous term and diffusion, or source term, and unsteady terms. But you already have it, as always. For diffusion, you can write this Laplace equation as a steady conservation law. And to do this, you need to introduce, this is one way, but the solution U and extra variables P and Q, they correspond to X derivative and Y derivative. And then you can write this as a hyperbolic system. And the same scheme applies. And for source term, you can look at this paper, but source term can be written as a divergence form, like a steady conservation law. You can define fluxes like this, so that you can write this whole equation, the conservation law with source, as a single conservation law, and that same scheme applies. And unsteady, you have time derivative, but if you use implicit time step, you have some kind of BDF term, and you often treat this as a source term. And source term can be written as a conservation law, so everything can be written as a conservation law. And the same third order edge-based scheme applies. And so third order edge-based scheme for steady conservation law applies to various equations, including Navier-Stokes. And I already have Navier-Stokes. But this is one approach. I'd like to mention there is another approach. So diffusion source and unsteady, something other than steady conservation law. This is the approach I just talked about. modify the target equation, and that requires extra equation, but the same scheme can be employed. And I already have this hyperbolic Navier-Stokes scheme based on this edge-based scheme. The other approach is to modify the scheme. It's not the equation. And it requires some extra computational work, but you can actually produce a very accurate scheme. And people they have this paper. In their paper, they show fourth-order viscous scheme with cubic least square gradients. So third-order edge-based scheme has already been demonstrated in Navier-Stokes. They have Navier-Stokes results, including unstable. Okay, so this is the problem. Edge-based discretization at boundary. If you can impose boundary condition strongly, you specify something, you don't really need this. But if you impose boundary condition as a weak boundary condition, like in the form of flux, and then you need to define the residual at the boundary node. And here's the edge-based scheme. So edge-based scheme, this phi J5 is flux across this, between J and phi, and across this place. And then J4, it's a flux divided at this midpoint times this area. And J3 across this place. And J2 across this place. So we have to close this residual by some kind of boundary approximation along these boundary faces. And these boundary contributions, this I call phi left, which is across this place, and phi right R is this right face. They have to be defined such that all of discretization is exact for linear, for second order, or quadratic fluxes. This whole thing. So you cannot just apply some high order quadrature along this face. It doesn't guarantee the we need a value. Okay. So this is the difficult part of this problem. You cannot just define a quadrature formula along this face. You have to look at the whole residual. And of course, the number of triangles, maybe 2, 3, 4, 5, 10. For general case, you have to prove this. And for second order edge-based scheme, there are formulas available, exact for linear fluxes, and available for triangle quads and tets and etc. and prisms and pyramids. And these formulas can be found in this paper or in this book, 82 page. So here I focus on triangles. So I just want to show the formula for the triangle. This formula, if you look at this, phi left, this flux contribution is a 5/6 times the flux at J times 1/6 times flux at phi. And same to the right face. This formula has been known for many years. And the oldest paper I was able to find was this ARWA 95. And for these fluxes at J and phi, the boundary condition is set in the right state or ghost state. And then the left state is the solution, current solution at this node. And then let the numerical flux determine flux. And you can find details on these papers. Now, the third order formula is not known at this point. And I just tried this second order formula for third order scheme to see what I get. And this is an advection diffusion problem on a high aspect ratio grid, irregular. And I look at the solution at bottom boundary. And on the right, this is the comparison of second order scheme and third order scheme with second order boundary quadrature form. And as you can see, it's terrible. Second order results are top of the exact curve. So second order scheme is very accurate. But third order scheme is not even second order. It may be like first order scheme. So second order boundary formula doesn't seem compatible with third order edge-based scheme. And we definitely need a formula for third order scheme. But this is a difficult problem. So problem is to find this phi left and phi right, this quadrature formula, so that this overall discretization is exact for quadratic fluxes. And how can I derive such a formula? I worked on this, but it's just difficult for arbitrary geometry, arbitrary number of triangles, arbitrary shape. And I have to look at the whole residuum. And this is very difficult. But then, I remember this word. You already have it, right? It's hard to believe. And I just couldn't believe because I don't have what I don't have. And I have terrible results. But I must have it somewhere. I just don't see it. So, to break this barrier, you have to free yourself. Reset your mindset. Forget about deriving the formula because you already have it. You don't have to derive it, right? And like I said at the beginning, you have to believe it. This is the first step. So I decided to believe it. I already have it. And look at what I have. And now you are going to experience how I was able to manifest what I already have. This is what I have, right? I showed you that this is a third-order edge-based scheme with, quadratic gradient. So, and this is interior extension. So this is also third-order accurate, right? And this is also third-order accurate. This is also third-order accurate. This is third-order accurate. This is third-order accurate. And then finally, this is third-order accurate. Believe or not, this is a boundary stencil. And I still keep this third-order edge-based scheme. Two triangles collapse to an edge. But it doesn't matter because I have still dual volume. And this formula doesn't change. Yeah.
Well, maybe I'm missing something, but then you have 1 over Vj, and Vj is 0, no?
No. Vj is
sorry, yeah.
So this shows that I don't need formula. I can just use the interior scheme, exactly the same scheme, with collapsed stencil. But to implement this into a code can be a little bit complicated because you need to have these collapsed zero volume triangles. And you have to form this edge-based residuum. So, but if you look at this form, edge-based discretization carefully, and how it looks on this collapsed stencil. By the way, this is, there are two nodes here, right? Because one node approaches this J, and the second node can be used as a ghost node to implement boundary condition. But if you expand this edge-based discretization on this collapsed stencil, you find these formula. So it just comes out from third-order edge-based scheme on this collapsed stencil. So I have a formula. This is very useful for implementation. So I call it general formula. It preserves first, second, third accuracy at boundary nodes because it's exactly the same as the interior scheme. And I need to explain a little bit here. The phi JB is between these two collapsed nodes. So node B serves as a ghost node. You specify boundary condition and compute the flux. And this phi J5 is a flux across J and phi. So it requires linear extrapolation to the midpoint. But normal vector, the phase normal, should be this normal. In the same way here. So third order scheme is achieved. Third order is achieved with straight boundary edges. There's no need to curve the boundary edge.
So, do you assume that the flow values are the same at J and B?
No. At J, I specify some boundary condition. At B.
With B.
Not J.
J and B, are J and B the same? They're the same point, so
Yes.
Q is the same.
it becomes in the convergence at the at convergent level. Yeah, numerical flux takes two values, left and right.
Right.
And the right value is the boundary condition value I specify. And the left value is the current solution I have at G.
Do you have to change your these squares at all to accommodate this?
No, but I need to have enough neighbors on that boundary. For quadratic least squares, I need neighbors of neighbors.
So you have to bias the, in a sense, you're biasing.
In a sense, yeah, you have to go move out, yeah. I need 3 points to be able to compute second.
But just a comment that for interior scheme, you may still need neighbors of neighbors just from stability considerations.
Yeah.
So you have enough neighbors, but from stability consideration, you may still, so it's not really any additional constraint.
But because you're using least squares, you're still going to suffer from the same ills on grids that have very high aspect ratio cells on a curved surface.
But for high order, the accuracy is actually better when you fit quadratic search, so it's less problem when you fit linear.
Yeah. So there's no reason. Okay.
What you put as a gradient for node B? You carry gradients.
Here, I don't need gradients because these two nodes are just the two values with no distance.
Right.
Just the left and right states and going to the numerical flux.
But they are not the same at the
They are
B.
not.
So what you put at the B for the gradient, because you carry gradient as variable.
The extrapolation
doesn't have to extrapolate.
I don't need to extrapolate. There's no distance to extrapolate. Just two
No,
values.
I'm talking about, because in hyperbolic formulation, you already, your gradient is one of the variables.
Yeah.
So we are P or Q that you mentioned.
Mm-hmm.
So what you put P or Q for B?
Oh. Okay. So that's okay. How to specify it? There are many ways to do this, I think. And
because at the surface you only have one, not the normal. You have the right. So what do you put for the normal?
Yeah. For the regular condition, for example, if you know the solution, you can compute approximation to the tangent.
So what about the normal?
Nothing. That's why you need this residual. And I will determine this normal component by solving this residual equation.
How do you set the value of in B in the boundary node?
There are many ways to do it.
But
I
so
don't
that
know.
you don't
Okay.
set, you don't set the gradient? They are zero, the gradient?
Yeah.
So if you want to specify a gradient of the temperature, suppose that it's a wall.
Oh, you can specify.
If you have it in Celsius.
Okay. This is just one way. Specify B. Another way is just forget about this ghost node. And you compute this flux by using the value specified by boundary condition. For example, if you have adiabatic wall, for example, the normal heat flux is 0. And then you set it directly 0 in this flux, physical flux. And you use it at this point, and no ghost nodes. That's another way.
But if you have velocity, you're carrying normal velocity component as one of the variables. What you put there, you don't know.
So in that case, I will solve this residual equation at the node to determine the value I don't know. Yeah, that's the point of this. Because if you can specify everything at the boundary node, you don't need residual. If you want to specify through the boundary flux, and then determine the solution by solving the equation, and then you need to do this. But
As you were collapsing, right?
Mhm.
You said you still have third order. Is that a guarantee? Is that a guarantee that you have third order?
I think so, because I see no reason why it loses accuracy.
Because now your gradients in those two triangles, right? They would be like as you shrink it. Like you were saying that even in the
Collapse.
interior stencil, when you have a mesh which is like element which is probably much there's a big gradient in sizes and this thing, then that local element, the gradient would be slightly lower order, isn't it? I mean, as like Boris said, it may not be as worse as like second round, but will it still be bad? I mean, can you go to the previous slide?
Like, least square gradient?
Like before, as you were shrinking,
yeah,
the ghost, yeah, like that. Is it still third order there?
Yeah.
Yes, this is interior scheme, so that's formally set up.
Yeah. For example,
Then he collapsed, so he still has set up.
yeah.
If you only have one gradient, it's the gradient of J formed by the stencil that's...
Yeah, but you know, as what I was saying is, like for example, to evaluate the flux with the other phases, you would still need I value and you need the I also, right? To get the flux which is going through that mid phase.
So in the interior, this third order was shown before. So
Okay.
for any small distance between 1 and J, it is third order.
Okay.
So in the limit, it is third order.
Okay.
Yeah. I see no reason why it loses like this. So using node-based finite volume scheme, somewhere in the interior, you can have zero volume, zero element. One triangle collapsed to edge. That's fine. Okay. So I have a formula, and I have some remarks. The same approach can be used to derive a formula for tetrahedral grid, and it is available in the paper. And curved elements should not be used because there is no reason why it requires curved mesh. So the edge-based discretization is third order on linear triangle elements, only triangle, and immediately applicable to existing grids. No high order grid generation is needed. And this is not the only third order scheme on linear elements. I know one third order fluctuation splitting scheme, and I know another one third order least square scheme, and I know third order residual distribution scheme doesn't require curved elements. I mean, curved elements shouldn't be used because these schemes are designed
For third order.
for third order.
Yeah, if you go higher order, so you have to use the...
I don't know, because edge-based is maximum third order, but fluctuation splitting scheme, for example, if you reconstruct like curvature, and then you can go to fourth order. But still it is a design. It is designed on linear elements.
Okay, that I don't understand. But
Yeah, but I don't know. I haven't done this.
But still, you are approximating your geometry in a first order manner with linear element, right?
Of course, yes. I will talk about this.
So the overall accuracy, if you want to sum up everything, could be still second order.
Yeah, I'll come back to this point in the results. I'm just saying you don't need, this scheme doesn't require curved elements. Okay, that's all I'm saying right now. But it does require some additional information.
You don't require curved element to see the design order, right?
Yeah.
Okay.
And so these schemes are attractive alternatives to high order methods, but in applications for which third order accuracy is, you think, sufficient. If it's not sufficient, sorry.
You don't believe? You don't believe?
Yeah, I have to. It's difficult. So from general formula, you can derive some special formula. This is a flat boundary, but non-uniform. On the left edge face, boundary face, and right boundary face, they have different lengths, but they are straight. And I call this ratio of the lengths called C. And in this particular figure, this C is 2. The right length is twice as long as the left one. And in this case, the general formula just reduces to these two formulas, the function of C. And this is not very particularly useful formula, but this is very interesting formula. Because if we think about flat and uniform boundary, if C is 1, what do we get? If C is 1, this term goes to 0. And this term becomes 6 divided by 6. So just one flux at J. And in the same way, if C is 1, this again vanishes. And this term becomes 6 over 6 and 1. So for uniform flat boundary, this 1 point formula, this is what I call 1 point formula. This is typically used for quadrilateral grids. And I never expected that this simple formula works for triangles. But this actually gives the order accuracy on uniform flat boundary. This was a big surprise. So here's a summary. I call it 1 point formula. This is first order in general for triangles, but third order for flat uniform boundary. And I have 2 point formula. This is a well-known formula for second order scheme, 5/6 and 1/6. And now we have this general formula that works for all schemes up to third order, 2/3 and 1/3. And here's the extrapolated computed flux at H midpoint. So now I'd like to show some results, but I only show third order results. I have second order results in the paper. And also I show Burgers and Albertian diffusion and Laplace equations. The results for Navier-Stokes is actually already available in other paper. And all equations solved as a steady conservation law. So I applied exactly the same scheme. And I typically use 10 irregular triangular grids up to 400,000. And the residual reduced by 10 orders at least in all cases. And errors are measured at interior and boundary separately to see the effect of inaccurate boundary form. So here's Burgers equation. I introduced source term so that the exact solution is smooth and nice sine function. And this is a square domain. And at the top boundary, I treat this as an outflow boundary characteristic going to the top. And I specify exact solution elsewhere. So as I show here, on the top boundary is irregular. It's not straight, it's not uniform. And some nodes go outside of this square domain, but that's not the problem. This smooth function is valid, even outside domain. So let's look at the error. This is boundary discretization error at the boundary nodes. So with 1 point formula, inaccurate formula, the third order scheme becomes first order scheme. With 2 point second order formula, the third order scheme becomes second order scheme. And only with general formula, you achieve third order accuracy at the boundary nodes. But in the interior, this is the error in the interior nodes. But in interior, this reduced order of accuracy doesn't greatly affect the accuracy in the interior node. With 1 point, it deteriorates, but 2 point general, almost the same, third order accuracy. This is probably because the error doesn't propagate back into the domain. The error committed at outflow and just go away or stay there. But this is a very special case, the scalar advection equation. So look at advection diffusion. Okay, so it has some advection, finite advection speed and finite diffusion coefficient. And I apply third order Edge-based scheme in steady conservation form. So in the steady conservation form, I compute solution U and 2 extra variables, P and Q, which will be Ux and Uy, the derivative of solution. And in this case, I treat this bottom boundary as a test section. And I have irregular mesh here. It's not even straight. And apply weak condition, but I specify solution U and X derivative, but I compute a Y derivative by the scheme at the boundary node. This is a model problem for viscous wall. So Q, the Y derivative, corresponds to the viscous stress.
Is there any reason that you need to have, or is it, do you need to have nodes outside of the domain? Not exactly.
No, I don't need it. Okay, I don't need it. I want it to look very bad. Okay, so boundary node. Again, with 1 point formula, we have only first order accuracy, and second with 2 point, and third order with general form. And now the interior is in the same way. With 1 point formula on the boundary, only on the bottom boundary, the interior discretization error becomes first order. And with second order formula in interior, it's entirely second order. So you really need this general formula at the boundary to keep third order accuracy everywhere. And that Vargas equation is a very special case. Even for the Euler equation, there is a acoustic system. The error propagates every direction in subsonic flow. Yeah. Yes. So, and here's the high aspect ratio case, anisotropic grid. So I just push this grid down, and it looks like this. But actually, I can expand this. You know, it goes from 0 to 0.01 instead of 1. And for this test, I used flat uniform boundary so that I can use 1-point formula for third order accuracy. And compare with 2-point formula, that's only second order accuracy. So this is the y derivative at the wall, bottom wall. And blue point is with 1-point formula, which should be third order. But red point with 2-point second order formula, so it deteriorates. And this third order Galerkin result is just as a reference, just to show that this high aspect ratio, the skewness is huge. And actually, if I zoom out here, in this region, you see that third order scheme, Curie's third order scheme, is this data on top of exact curve. But with second order formula, it's really bad. And this third order Galerkin, it's not a Galerkin. Solution computed by Galerkin, but gradient computed by these squares, quadratic.
Hiro?
Yeah.
Just a curiosity, why the red bullets are all off, but the last one is on top of?
Oh, that's specified.
Oh yeah, because the mountain.
Yeah, at the corner. Yeah. Because at the corner, 1-point formula is not exact for third order because it's not flat.
How many equations did you have to solve in this instance?
How many equations?
Yeah.
For advection diffusion, 3.
3. Because of two derivatives.
U, PQ, yeah.
Yeah, viscous.
Yes.
Okay, that's what I thought.
Okay, so I really need this third order boundary formula. And now the last example is a curved boundary problem. It's a very simple problem. A potential flow over a set. Here's the exact solution, the streamline, and this is, I think, the contours of the x velocity. And I have fully irregular grid. The node spacing around the cylinder is non-uniform. It's irregular. Here's a very small space. And governing equation is just the Laplace equation for the stream function. And third order Edge-based scheme applied, and it's steady conservation law form. So this has solution u and x derivative and y derivative as variables. And in this case, it has physical meanings. The y derivative is the x velocity, and minus the x derivative is the y velocity. And this third order Edge-based scheme produces third order accuracy in all these variables. And boundary condition. Out of boundary for simplicity, I just specify that solution. And cylinder. On the cylinder, this is the force. I know the stream function, which is 0, so I specify this is a Numerical strong condition. And I also know that there's no flow into the cylinder. So this is actually normal velocity. Is 0 at the node. And the third equation, this is a residual. This approximates the tangent condition. The tangent velocity given by P and Q must be equal to this stream function derivatives. And this is where I need this boundary flux because I define the residual at the node. For these two, these are strong conditions. And this is the very important point. Typically, I use the linear approximation. The normal vector here is computed by using these neighbors, just the difference. But this is not a very accurate norm. And I need this norm to implement those boundary conditions. So I have also quadratic approximation. I take these 3 nodes and interpolate by a quadratic function along the length, along the parameter, in the parameter space. and then differentiate to get this tangent and norm. This is reconstruction, and I don't need analytical geometry.
But you need to know this curve, right, to interpolate along this curve.
What do you mean by curve?
So you have high order curve along which you interpolate. So you need, in this sense,
I need 3 data points.
and then you, for third order, and then you fit quadratic
Yes.
curve here and you interpolate. Okay.
Yeah.
Okay.
So I don't
So
need.
okay, this is your way to use curve approximation, second order approximation to geometry.
Yes. So I said I don't need elements, but I need some information about curvature.
Well,
And-
but that's all you need also in DG formulation, right? If you get the normal right, you don't need to have curved element. So
Okay.
here
Yeah.
basically what you're constructing a
There's
better
no-
normal.
Yes.
There is no magic, so it's just, so that's what you need.
Yes.
Except in this case, I think this is similar to the Cradonova's approach, right? That's what they're doing too. They don't use
Whose approach?
Cradonova and
Krivonodova.
Krivonodova.
Yes.
They're doing similar.
Right.
They're fitting that.
Yeah, they keep the linear edge, but they change the normal.
Yeah.
That was Marcia Berger's student, right?
Yeah.
Yeah.
So they implement something like this.
Yeah. Yes. But I only need at the node. And just one point. Not along this edge. And of course, if you have a corner, some geometrical singularity, you have to do some special treatment because you don't want to interpolate quadratically over a sharp corner. Anyway, this is a smooth problem. So linear approximation. And this is discretization error.
So what do you do in corners then? So you need 3 points?
I don't have a corner.
Yet, or you, in this?
For this work, no.
He's got a circle.
Right. But in corner you use 3 points, you just use one-sided stance?
I'm saying at the corner.
You believe you have a circle.
You can do anything. But at the corner, I mean, this sharp corner is a geometrical singularity. You don't want to smooth it, right?
So how you have third order approximation for your norm?
I don't know yet.
Okay.
But I believe I can do it. Strongly believe. So linear approximation is bad. Okay, on the boundary node, I don't get third order accuracy for any of the formula. So it's almost like first order scheme, a little bit better than first. And it does affect the accuracy in the interior. So I don't get third order accuracy, just second order. And it seems like getting worse. And using quadratic approximation at the boundary, I get third order with general formula. But 1.2 point, this is not enough, even with quadratic approximation. And there's no effect on the interior accuracy. So only the general formula gives third order accuracy with a sufficiently accurate normal vector. And here's the solution. With 2-point formula and the general formula. With 2-point, something's wrong here. You can see the contour has some irregularity. It is not very accurate. But I'm saying this is on a relatively coarse mesh, but it gives a reasonable solution. There's no strange behavior here based on the edge, straight edge. Because edge-based scheme is like a finite difference scheme at the node. And it does approximate the governing equation with sufficient accuracy at the node. Anyway, so conclusion. Edge-based scheme is first, second, third order through boundary nodes. And we already have general quadrature formula. And numerical flux should not be exact for quadratic fluxes. And third order accurate without curved elements. But accurate normal vector is required for third. But this can be reconstructed. And more details can be found in this paper. And finally, another important conclusion drawn from old study is, since Christmas is coming next week, you don't have to worry if Santa Claus doesn't bring you any present, because whatever you wish for, it already happened. Thank you.